Water Tower Final Presentation by Ethan, Robert, Avery, and Nathan. ESG 260, Professor Emmy Tomfort. During this presentation, you will visually see each one of us and hear our voices. Our vision. We aim to make a super simple design that can be built with readily available materials. By making a simple design, we make it more plausible for the locals to continue building the same style water towers and therefore help them grow their city. Also, by making the water tower with readily available materials, we hope to bring down the cost of the water tower, making it more affordable for the town. By helping the locals, we aim to fulfill our duties as good, God-fearing people. Lack of drinkable water. Over 2 billion people globally do not have clean water to drink according to UNICEF. Some of the most affected regions are Sub-Saharan Africa, parts of Asia, and parts of Central America. This map shows parts that have running tap water but do not have clean drinkable water. The city that we chose to implement our water tower is in Bagral, Somalia, where although they face several other hardships, we plan to help with their clean drinkable water issue. Economic and social impacts. Aside from all the obvious health risks of not having drinkable water, there's also another impact like social and economic hardships that may fall on towns who do not have drinkable water. According to the World Bank, countries that struggle with having drinkable water for their residents or citizens may see a decrease in their GDP by as much as 6% by the year 2050. This would directly translate in a slower development in places that struggle with providing their residents with drinkable water, like the town of Bagral that we chose in Somalia. Project in harmony with Christian values. Building this water tower in Bagral shows our commitment to our Christian values. For example, compassion and empathy. This design focuses on addressing the needs of the most vulnerable, reflecting Jesus' teachings on caring for the less fortunate. Stewardship of resources. This ensures responsible use of all resources, promoting sustainable and care for God's creation. Community and fellowship. Encourages community involvement and partnership, fostering a spirit of fellowship as guided by Christian teachings. Even though it may be hard to do so in this region, it is our duty to keep trying. Service and sacrifice. Prioritizes selflessness, service to others, echoing the Christian call to serve rather than to be served.
So our design for the water tower project, we went by the motto given to us in class, which was KISS with an additional S for Keep It Simple static students. And with that, we really took that to heart, and we came up with 2 designs that were easy to model. Our main goal was to make it 1 layer so that we had less members to find forces of, and also the minimal height led to smaller moments on the structure. Along with that, the theme of going along with making it easy to model, instead of making a round tank, we made this tank square. Because we were able to do that because there was so little water in the tank, it just makes more sense to make it square, especially looking up all the ones online. A 300-gallon tank was square. And additionally, our final 2 designs that we went on to was to have a square truss and a trapezial truss that you'll see further in the presentation.
We're using a cube tank because this is simpler to model. This is going to be made out of galvanized steel. And then we have a 1-layer high truss as seen over here. That's just simpler to model. It has less members to analyze. It's a cheaper material cost. We're using AISI 1020 steel, which is readily available. We are also only making it 1 meter tall due to the lack of a height minimum. And this lessens moments on the truss and and it's simpler hand calculations for all of us. This is going to be our global free body diagram of the first design, our square truss. We have our roller at A as well as our pin at B, and this global helps solve for those. For the wind force at the top left, that was calculated using the average wind speed in the area. The force of the water at the top was the water alongside the tank as well. You have C1 and C2, those are going to be our two cuts, which we'll see in the next slide. These are our free body diagrams used to calculate our truss forces. So in the first cut, we're using AY, which we calculate with the global, and we're finding FAB, FBD, and FC. And the next one, we're using that FAB and FBD, and we're calculating FBC. And then we're also going to go on to the next cut, which we're using FAB from the first one, as well, and to calculate FAD and FDE. And finally, we're doing another joint, and we're calculating FAE as well as FAD. Our second design is our trapezoidal truss. This is using a rectangular tank, also made out of galvanized steel. And then we are using a one-layer high truss, similar to the first design. This is, again, less numbers to analyze. Although this truss features a wider base at 4 meters. This is because it is obviously a wider base and more material, it is going to be more expensive. And this is, again, going to be only 1 meter tall. This is our global free body diagram for design 2. It is going to be with our roller at A as well as our pin at C. The global, of course, is going to help us solve for those reaction forces. We also have 3 cuts on this one as opposed to 2 on the previous, just due to it having more members. And then the wind force is staying the same. The force at the top, due to the water, is obviously going to be heavier because of the larger tank and more water that it can hold. Because each of the triangles have a side length of 1 meter, that made it also easier for us to calculate the different forces due to them being 45, 45, and 90 triangles. For these free body diagrams of design 2, we only used method of cuts, no method of joints. And we're looking at finding FBC, FBF, and FEF on the first one using our reaction forces found at the pin of C. And then moving on to the second one, we again have 3 unknowns, so 3 equations, and we're using that AY force that we found earlier in the global. And then finally, we're going to be using the FBD and FBF to find FAD, FBE, and FCF.
All right, so now getting on to the meat and potatoes of the presentation. The whole point was to simulate it under real world conditions using wind speeds. So the first thing we did in the solver simulation was to do it with initial conditions. These initial conditions were with no wind on both of them. One of them had half capacity of the water and the other had full capacity of the water. Both initial conditions were known for both designs, a total of 4 initial conditions. Following that, we did it under real world conditions, or what we're calling real world. With this, we modeled the average wind speed as a point force on the left side of the truss at the top of the truss. For the first real world condition, we had average wind speed and half capacity. The second one was average wind speed and full capacity. The third and fourth were both with double wind speed, half, and full capacities. So for both designs, altogether, there was 8 simulations with the real world conditions. We used these conditions then to compare it to our hand calculations that we used our FBDs on, and to get a percent error to see which one was more accurate. On to part 2 of our simulations. Here we can see what it looks like in SOLIDWORKS when you do a simulation. On the simulation, we're able to model our force of the water directly onto that joint, and we also have our force of the wind at the top of that structure. Then on the bottom, we're able to model a pin using an immovable fixture, and that prevents the translation of both the X and the Y. Then on this pin on the left side, we're going to have, it's called reference geometry, and it's on the top plane facing upward. That prevents that translation going into that ground. From these calculations, we're able to calculate using the wind speed In our location in Somalia, the wind speed was approximately 7.02 meters per second, which then, when we put that into a wind speed calculator, that's about 30 newtons of force. Other than that, after completing the simulations, we found out that our SolidWorks simulations almost perfectly lined up with our hand calculations, having a percent error of 0% on all of them, except for force member BE. Force member BE had a percent error of 100%, which seems like kind of a problem, but it's simply because of an error, or not an error, and differences in loading the truss as we did by hand and on SolidWorks.
Alright, after a few pots of coffee and a long analysis conversation, we chose design B because it has a larger base which allows for a more evenly distributed load, and this design can hold more water because of a bigger tank. As explained earlier, we used two materials which consisted of AIS 1020 steel and galvanized steel. For design A, which is our square truss, the total cost came out to $890, and for design B, it came out to roughly $1,500. However, design B can hold more water.
Final drawings. So for this slide, we put together the drawings for design A and design B, even though we already chose design B. Man, I'm out of breath. For design A, essentially these final drawings are showing the final dimensions and final angles for the trusses to be put together. These final drawings will help our people when we send this in for them to put it together and verify that it's put together correctly. With this, they will use the directions we attach to the project, and they'll be able to put this tower together, lickety split, and have clean water. In the end, we have our conclusion. Thank you for coming to our presentation. In this presentation, we discussed two designs of a water truss tower to help the Somalian people have clean drinking water. The goal was to make a tower that could hold 300 gallons of water to give them 2 days worth of water. We performed rigorous calculations and simulation to make sure that our tower and our structure was up to par, and that any wind conditions that it experienced, it was still able to stand true and hold. In those calculations, we found that our SolidWorks and our Hound calculations almost perfectly matched up to have 0% error. On to you, Nate.
Design B was ultimately chosen, and in short, the reason being that more water equals more healthy people. And as good, God-fearing Christians, we want to help as many people as possible. On to you, Avery.
In the long run, we will allow these people to save money, and we will also promote them a healthier life because they have clean water.